sort of polynomial that we can write. Here's a power series centered about x equals c. Power series centered about x equals c is an infinite polynomial that looks like the sum. Let's see, I'll use n's as my subscript this time. We'll have coefficients of the polynomial and then powers of x minus c out here. We'll start at n is 0 and go to infinity. So they look like a0 plus a1 times x minus c plus a2 times x minus c squared, a3 x minus c cubed, you know, like a polynomial. Where these numbers a are real numbers that look like the terms in the series that we have been working with. And what we're interested in finding is the interval of convergence. These things will either converge over an interval that's either closed, open, or half open, or half closed, or they'll converge only for a single point, or they'll converge over the entire number line. And we'll find the interval of convergence using a ratio or a root test. They will converge. They will converge over an interval or over the entire real number line, which is an interval from minus infinity to infinity, or at a single point. We'll find this interval of convergence using the ratio or the root test. Generalized ratio or root. For the generalized ratio test, we solve the absolute value inequality where we take the limit of the n plus first term divided by the nth term. And we're trying to find where that's convergent, so we're going to set it less than 1. So we're going to look at the limit as, I'm using an n today, n goes to infinity of the a n plus 1 x minus c to the n plus 1 divided by a n x minus c to the n is less than 1. Okay, so we solve that for x. Because we know if the series has a limit smaller than 1, it converges. If the limit's bigger than 1, it diverges. If it's equal to 1, it's inconclusive. But we want to know where it converges. So here's kind of a short one. We're going to find the interval of convergence of So our first one is going to be the sum from n is equal to 1 to infinity. One over n times x to the n. So I chose my c to be 0. This would be a power series centered at the origin. And I had to start at 1 since I'm dividing by n. Where I start doesn't matter. But this looks like the polynomial 1 over 1 times x plus 1 over 2 times x squared plus 1 over 3 times x cubed, and so on. Now, if this x weren't here, we've got the harmonic p-series, so it doesn't even converge. So we're going to see if we can fix that by putting some values in for x to make that converge. Okay, so here goes the ratio test. I'm going to set this up. We're going to look at the limit. As n goes to infinity, let's take each of those n's and increase them by 1. So let me write that as a single fraction. Say x to the n plus 1 divided by n plus 1. Now we're going to divide by that term. So we jump to the step where we flip it over and multiply. And then we're solving this inequality. And the only thing that cancels is the x to the n. And it leaves me an x to the first power right here times n over n plus 1. So I'm going to write like this. I got an x to the first power. I'm going to pull it out of its own with its own absolute value bars. And then I've got n over n plus 1. And then I want to find where that's smaller than 1. So this has nothing to do with n, but this does. It's an expression where the degree on top is the same as the degree on the bottom. So I know that this limit is just the ratio of the coefficients. This has a limit of 1. So I'm solving the inequality. The absolute value of x is smaller than 1. This number 1 here is called the radius of convergence. It's describing an interval around 0, 1 unit in each direction around 0. It says that here's 0. I go 1 unit that way or 1 unit that way. I know that my power series converges inside of that. Now we want to see what happens at the particular endpoints. So far, we have that x is between -1 and 1. But we'll need to check the endpoints to see what happens to the power series at those. We're going to go back to the original series, and we're going to replace x with each of the values at the endpoints, and then test that series on its own. So at the left-hand endpoint, we're replacing x with -1. Right here, we're going to test x is -1. We have the series -1 to the n over n. Can anybody tell me about the convergence or divergence of this series?
Is it convergent because it's an alternating p-series?
Perfect. This is a convergent alternating p-series. All alternating p-series converge because they all have a limit to 0 and they all decrease. So we're going to include that endpoint. Now we check the other one. Let's test x is equal to 1. So when I put a 1 in here, I have the series 1 to the n over x to the n. 1 to any power is 1, so we just have, oops, not an n, not an x, I want an n. Right here. N. So I just have 1 over n. And this one? That's a divergent p-series. So our conclusion is that this is our interval of convergence. And I think on web work you write it as an interval. So we would write that as closed on this side, open on that side. What it converges to, we don't know. We don't care just yet. But we know that it'll converge to some function over that interval. So let's try another one, shall we? All right, let's just change it slightly. Let's go with an x to the k here. We'll put a k factorial down here. Oops, I changed to k. Sorry about that. This time I can start at 0. The 0 factorial is defined to be 1. So start the same way. Put your ratio test in there, set it smaller than 1, and solve for x. X to the k plus 1, divide by k plus 1 factorial. And then we divide by that, which puts the k factorial here and the x to the k here. Set it smaller than 1 and solve for x. So we can go ahead and cancel this one with that one. Leaves me an x again that I pull out on its own. And then I leave my k's in here. And so how does the k factorial cancel with k plus 1 factorial? There's going to be a k plus 1 on the bottom. That knocks off all the factorial behind the k plus 1. So I'm just left with 1 over k plus 1 in here. Agree? So what's that limit? That limit is 0. So here's what we get. We get the absolute value of x times 0 is smaller than 1. That's going to be true no matter what x is. This holds for any value of x. So this is an example where this power series converges over the entire real number line. So our interval of convergence is from minus infinity positive infinity. Okay? All right, so let's now move it a little bit away from 0. Let's find the interval of convergence. K factorial x minus 2 to the k power. So here we go with the ratio test. We got a k plus 1 factorial x minus 2 to the k plus 1. And I can go ahead and divide k factorial x minus 2 to the k. So like before, we did some cancellation here. This knocks out all of the x minus 2's except x minus 2 to the first power. Then this knocks out all of the factorials. But that leaves me a k plus 1 on top. When that happens, this limit becomes infinite. So no matter what I choose for x, I can't get the left-hand side smaller than 1, unless I make this power series disappear altogether. If x is 2, I'm adding a bunch of zeros together. And when I do that, I have a convergent power series that converges to 0. So this is an example of a power series that converges at a single point, and that's at x is 2. Okay. So you get convergence over an interval if your limit is some number bigger than 0, but smaller than 1. Or big to some number that's not 0. If your limit is 0, then it converges over the whole number line. If your limit is infinite, then it converges only at the value of x that makes this term 0. Okay? All right, so let's do another. Let's go with the sum. K is equal to 1 to infinity, negative 1 to the k, k times x minus 3 to the k, all divided by 4 to the k. Now, if this guy wasn't here, I would do the kth root test, because everything else has a kth power. But the presence of that one tells me to go back to the ratio test. Okay, try it. Let's see if you can get at least the radius of convergence. But you guys can simplify this one. see what they got. We're running out of days awful quick. We don't need to do it. It's that learning thing. You know, it's the point of college.
I'm doing much of
I'm telling your family, they're gonna pull that tuition money. We're here only for the fun. Fun is in the money. Right?
Whatever you say.
Whatever I say.
Or to learn, you're going.
You traveled all this far to do some learning, didn't you?
Right.
A little bit. Make sure you get set up the right way. That's where we're starting. It's big and long. Let's see how much you got to cancel. Okay. Okay. Think you're good. Think you're good. So far, so good. You cancel along with you. -1 to the k. Cancels all of those. And I got a -1, but it's an absolute value, so let's go ahead and get rid of it. Then I've got these guys knocking off all of those. This one knocks off all of those. That's all I got. So -1 is going to be gone because of the absolute value. I've got the x minus 3 to the first power by itself. And then a k plus 1 on top. And a 4 to the 1 on the bottom times k. Finding where that's less than 1. Did you get that far? And what'd you say this limit was? 1/4. So now we're solving the inequality x minus 3 in absolute value times 1/4 is smaller than 1. So I'm going to multiply both sides by 4 and get that my radius of convergence is 4. So again, that's describing a region on the number line. I'm centered at x is 3. So here's x is 3. I can go 4 units that way and 4 units that way. And that interval contains values of x that make this power series converge. 4 units on each side of 3. So here's another way of saying this. That says that x minus 3 is smaller than +4, but bigger than -4. Right? As I described, here's 3. Go 4 units that way. Go 4 units that way. And so that says x is smaller than 7, but bigger than -1. All numbers in there, this power series converges. Now we're going to check what happens at each endpoint. substitute values of x. We're putting in, say, x is -1 right here. Let's rewrite that series when x is -1. I get the sum from k is -1 to infinity of -1 to the k, -1 minus 3 to the k, all over 4 to the k. Substitute -1 in for x. That last term out there is a -4 to the k. You can think of -4 to the k as -1 times 4, all to the k. And with our property of exponents, I can put the -1 to the k and a 4 to the k. So I'm going to rewrite that. That cancels the 4 to the k's. And how do you multiply -1 to the k with -1 to the k? It's going to be +1 because you add exponents, get -1 to the 2k, which means -1 squared to the k, or 1 to the k. So that's just 1. This multiplies to give us 1. This cancels. So the series we get is this. Does that series converge, the sum of all the k's? No, it diverges by the test for divergence. Its general term does not go to 0. So that endpoint is open at x is equal to -1. Now let's see what happens when x is equal to the other endpoint, when x is equal to 7. So I'm going back up here, and I'm replacing x with 7. So I have -1 to the k, 7 minus 3 to the k over 4 to the k. So that 7 minus 3 becomes 4. The 4 to the k's again cancel. And this time I have this series. What do you know about that one? The general term still doesn't go to 0. Right? In the alternating series test, we need that term to go to 0. So it's also going to diverge. So we have an open interval. Our interval of convergence is the open interval that I have written up there. Okay. So that's the point of this section, to see if you can find the interval over which a power series converges. In the next section, we're going to start using them. And one of the main theorems that we have is on its interval of convergence, The derivative with respect to x of a power series, I'll just write the general one, a n x to the n, can be done term by term. The derivative of a power series can be done term by term. And so if I have here, this goes from n is equal to 0 to infinity, then the derivative, so if I take the derivative of that in general, I have this term here, I bring the power down, I raise it to 1 power less. Now I move this up to 1. Because I don't want to have because remember what this means? It means a0 plus a1x plus a2x squared plus a3x cubed, and so on. So the derivative of the first term should be 0. So I wanted to make sure that I didn't get an a0 term. And then my derivative of the second term is just going to give me an a1. If I substitute 1 in for n, I get a1 here, but 1 times x to the 0 is just 1. So taking the derivative term by term jacks the counter up by 1, and then gives you that. We can also take the antiderivative term by term. That's a big deal. We spend a lot of time in say, our advanced calculus class saying, when can I shift places between these two guys? When can I shift places between those two guys? If that's equal to the sum of the integral of each term. We can also do term by term substitution. If we define this thing as some functions of x, we can do term by term substitution. So also, if f of x is the sum from n is equal to 0 to infinity of a n x to the n, then f of u of x can be done term by term. Schovanec's interval of convergence. So I want to show you something pretty cool with an earlier example that we did. Let's go back to that power series that looked like x to the k divided by k factorial. We said that thing converged over the entire number line by doing the ratio test. Let me write this out. This means 1 plus x over 1 factorial plus x squared over 2 factorial plus x cubed over 3 factorial, like that. Let's call that function f of x. And let's take the derivative of it term by term. So I'm looking out over there. So when I take the derivative of that first term, I get 0. When I take the derivative of that, I just get 1, because 1 factorial is 1. I take the derivative here, and I get 2x over 2 factorial. Here, I get 3x squared over 3 factorial. Next term, 4x cubed over 4 factorial. So if I squeeze inside here and take the derivative, I get kx to the k minus 1 over k factorial. And so we make the first term disappear. I can leave it at 0 since I wrote out the 0. But I'll just do it like that with the hay. I'll leave it at 0. You give me that term. Now I want you to look at this more closely, like this close. What happens with 2 divided by 2 factorial? 4 divided by 4 factorial. K divided by k factorial. Right? Do you agree with that? The k factorial is the same as k times k minus 1 factorial. The k's will cancel. And so this cancels here, just leaving me 1 factorial. This cancels here, leaving me 2 factorial, and so on. And that's why I need to start this at k is equal to 1 now, so that k minus 1 factorial will be defined. So it looks like 1 plus x over 1 factorial plus x squared over 2 factorial plus x cubed over 3 factorial. Where have I seen that before? Let me give you a big hint. Where have I seen that before? That's what we started with. Do we know any functions whose derivative is itself e to the x? What's the integral of e to the x? Let's integrate each of these terms, term by term. Term by term, so I'm going up here. I'm integrating the 1, and I get x. I'm integrating this, and I get x squared over 2 times 1 factorial. I'm integrating this, and I get x cubed over 3 times 2 factorial. And so on. And do you know that when you do an indefinite integral, you also get a constant of integration? What is 2 times 1 factorial, 3 times 2 factorial, 4 times 3 factorial? Well, this means 3 times 2 times 1. This means 4 times 3 times 2 times 1. So that is the new factorials. So here's my constant of integration. And then I have x over 1 factorial, x squared over 2 factorial, x cubed over 3 factorial, x to the 4th over 4 factorial. So again, I get the same function back. That's the power series representation for e to the x. So Well, okay, that's no big deal. But here's a really big deal. I don't know how to integrate e to the x squared. I know how to integrate x e to the x squared, but not e to the x squared. Well, suppose I want to integrate e to the x squared. I construct the power series for e to the x squared using the power series for e to the x by replacing each x with x squared. Then I integrate term by term in the power series. And if I have a definite integral, I can get whatever accuracy I want just by tacking more terms on there. So we can use the power series to give us values of definite integrals that we don't know how to integrate in closed form. You'll use power series in some of your differential equations techniques. You're looking for a function that has certain characteristics given by an equation, where derivatives of a function add together in a certain way. And you don't know what the function is. So what you're going to do is you're going to substitute a general power series in there and find what these numbers have to be so that that differential equation is solved. So when you're in your 3350 class, about this time of the semester, you'll be doing power series solutions to differential equations. And you'll be just taking for granted that you can take derivatives term by term and antiderivatives term by term. But it's a big, big deal. In the next section, we're going to go the other way. We're going to start with a known function and using a formula, generate a power series for the function. Here we just accidentally stumbled into a function that has that particular power series. But we're going to go the other way. We're going to build our own power series using something called Taylor polynomials. And it's real easy, and it's real fun, and it's a joy for everybody. But that'll be next time. Now for the rest of class times, I wanted to have you guys work on the handout that I sent you. Send it through email. If you ran it off, great. If you didn't, I have some. And I wanted to just come around and give you some hints and clues and corrections and stuff like that. So it's labeled series worksheet. Does anybody need a copy of it? It's also available for free on Blackboard. This means you guys just ignored my email? What if my email said, help, I'm on my deathbed, I want to see you one last time? I didn't know. Now, also on Blackboard, there is something called Positive Term Series Review, which gives you all of the series tests that we've had so far. If you haven't run one of those off, I have 5 of them available. Does anybody want these? There. Thank you. Anybody else? I got one more with a big smudgy finger on it. Smudgy finger. Okay, so in the first 2, we've got a series and then a similar looking sequence. So to see if a series converges, you've got to use one of our convergent series tests. To see where a sequence converges, well, what do you know? What makes a sequence converge? If it has a limit, just take a limit. If a sequence has a limit, that's what it converges to. Right? So for number 2, you're just worried what happens to that as k goes to infinity. Whatever it does, that's the value of the sequence. But for a series, if you want to know what its value is, there's only 2 kinds of series whose value we can actually find. The telescoping or the geometric. Well, that one's not telescoping. because there's no subtraction going on anywhere. So the first one's a geometric series. So run the geometric series test on it and see if it converges, and then you can use that formula to see what it converges to. So what did you decide the limit of this was? Is 0, because bottom goes faster than the top. Or if you wrote it as a single fraction, as long as this guy inside the parentheses is smaller than 1, it's going to converge to 0, because it's bottom heavy. So the sequence converges to 0. That gives us the go-ahead to check if the series converges. Because if my sequence, say, converged to 5, then I'm done with this as well. I would say that this diverges by the test for divergence. But having a limit of 0 means to go on. And like I said, if you want to find the sum, that's a clue that this is a geometric series. Another clue is a geometric series is I could write it like that. A constant raised to the k power. And so if I write out the first few terms, 4/5 to the 0 is 1. Then I have 4/5 to the 1, 4/5 squared, 4/5 cubed, and so on. So it's a geometric series where r is equal to, what's my multiplier here? 4/5, right? Smaller than 1, so it converges to, do you remember the formula? Not, it's on the little sheet I gave you. A over 1 minus r. What do I mean by A? A in this example is 1. It's the first term. So 1 over 1 minus 4/5. That's 1 over 1/5. So this thing adds up to 5. Okay. Okay, so now try the next three, and then I'll walk around, give you help. Try the next three problems. That's perfect.
Over.
We'll go through the same. Number 4, almost any test will work except for the ratio. You can do an integral test. You can do a direct comparison test. You can do a limit comparison test. Number 3, any one of those 3 tests will work. You can integrate it. That's easy to integrate. The series does what the interval does. It looks, you throw some terms away that looks like a basic series, then you can try one of the comparison tests. Either comparison test will work. one of those three. Sure. What gives you the respect for that? And then we also have the S is bigger than that, because we're driving this super slow. We have different divergence and divergence. We do direct comparison as well. That's what it stands for. Direct comparison test. Just to get you started in the right way, let me show you each of these tests. I look at this and I see that I can integrate it pretty easily. I integrate from 1 to infinity, 4 over 5x minus 3. I'm going to get some version of a logarithm. I'll have a 5 here if I do a UDU substitution. And then when that's in there, I get that this integral diverges. The integral diverges, so the series diverges. So when you're doing the integral test, make sure you compute the integral. And then show me that the antiderivative diverges at the upper limit or converges given the case. Yes, sir.
Why is 4 over 5 on 4?
If u is equal to 5x minus 3, then du is 5 times dx.
Oh, right.
So that 5 comes from the du substitution. Okay, then I said you can also use either a direct comparison test or a limit comparison test. We can compare the given series. If this 3 weren't there, it looks like 4 over 5 to the k. So for a comparison test, we compare it to the series 4 over 5 times k, which is 4/5 times 1 over k. So that's a divergent p series. The series that we have is larger than 4 over 5k because I'm dividing by less. I'm dividing a smaller number into 4 than I am here. And so I have bigger than divergent is divergent. That's the direct comparison test. So that's another way that it shows that it diverges. If the direct comparison test works, so would the limit comparison test. In the limit comparison test, we just take the ratio of the stated series and the lookalike series. And if you get a positive finite limit, they both do the same thing. So the limit comparison test for this particular one is also pretty quick. So we can do a limit comparison test using the same BK. So I take the limit of 4 over 5k minus 3 divided by my BK term, and I get 1. Any positive finite limit, they both do the same thing. And since I stated over here earlier that that diverges, then I can state that my series diverges. Okay? When you're doing the integral test, do the entire test. Don't stop here and say the integral is going to diverge. Show me what the antiderivative is. Then I can see whether or not it diverges. Direct comparison test. Tell me what you're comparing it to. Tell me what your comparison series does. Run the direct comparison with your conclusion. Either bigger than divergent is divergent, or smaller than convergent is convergent. Some of you on your homework, when you did the integral test, you stopped here. The integral was either convergent or divergent, and then you didn't give me the conclusion. I need this one sentence. Integral diverges, so the series diverges. Don't make me guess. The same deal here. With the limit comparison test, tell me they both do the same, and then you would say, since my BK diverged, my given series diverges. Okay? State your conclusion. Super. All right, the next one doesn't need any more room than I put right there.
I said no, then maybe.
Maybe? No, maybe what? Maybe is not a choice. Converge or diverge is essentially the answer. Maybe is not a choice. Maybe won't even get you partial credit. Converge or diverge, maybe.
What do we think?
I see a big old fat K cubed on top and a very slow natural log of K on the bottom. Top heavy. Doesn't have a limit that goes to 0. If the limit doesn't go to 0, the series has to diverge. Okay? Limit doesn't go to 0, so the series diverges. So this one we're doing the test for divergence. All right, so I'm taking the limit. K goes to infinity. K cubed minus 3k over 1 plus ln k. And that's infinite because it's top heavy. And since the limit is not 0, the series diverges. Give me your test, run your test, state your conclusion. You gotten to number 5 yet? Number 5 is very similar to number 3, except I don't want to integrate it. I do any comparison test. Because if you just start throwing some of those constants away, you're going to get a known series to compare it to. And then whichever comparison test you enjoy, try it. And then state your conclusion. One of your 2 comparison tests. Try this one. Go into 9, go into 1, come in a series of graphs, and then compare it to the comparison tests. Good. Does it converge? Yes, because that's what happens in one. Okay, then keep going with your limit comparison test. Positive finite limit and then series will do the same. Good. What kind of series is one of the Okay. It's geometric, constant to the k power. So all you do is look at the size of your multiplier, decide whether your comparison series converges. Good. Now do either comparison test or limit comparison test. See what your series does to it. It behaves like 1/2, okay. In the direct comparison, that is your side. This one converge or diverge? Let's do what's R? R is smaller than 1. R smaller than 1. Converges. So we have the comparison test. You have your series smaller than convergence. Smaller than convergence. There you go. That's right. That's right. Good. So I think in number 5, either a direct comparison or a limit comparison test works. I'll do a direct comparison test first. I'm going to form my BK series by just throwing away the 1 and throwing away the 9. So I made the numerator larger than that numerator. I made the denominator smaller than that one. So if I'm dividing something larger by something smaller, then I have something that got bigger. So I have that my BKs are bigger than my AKs. Also, my BKs simplify to the series 1/2 to the K. And I recognize that as a geometric series where my R is 1/2. Geometric series will always converge if R is smaller than 1. So now put these two together. I have my series is smaller than a convergent series. And the direct comparison test says that smaller than convergent is convergent. So that's the direct comparison test. Smaller than convergent is convergent. Now the limit comparison test says about the same thing. In the limit comparison, we just take the ratio of the two. So for the same problem, the limit comparison test, if you get a positive finite limit of the AKs over the BKs, then they both do the same thing. So if I left it in its unsimplified form, maybe I could see what cancels better. I I don't think I need that. I can go with this. I can go with the simplified form. That just makes a mess. Right? So this numerator will behave something like k times 2 to the k, and so with the denominator. The other ones will be lower in power, right? The other term would just be a 2 to the k and a 9 times k. Those don't grow as fast. So the controlling terms the same top and bottom, which means this limit is 1. So in the limit comparison test, positive finite limit means both do the same. And then over here, we decided our series converges, so both will converge. Things that look like almost a P series, polynomial type terms, or power type terms, divided by, or geometric series, work really, really well with comparison tests. Okay, so the next two, I think, jump out more obviously what you want to do to them. So let's do 6 and 7. On this one, are you guys jumping on this right quick? Get rid of k powers by doing a kth root test. Try a kth root test here. Take the limit of the kth root of the general term. The size of the limit tells you whether or not it converges.
Isn't it divergence often?
Let's see, if I take K through here, the limit is 1/3. The limit's smaller than the limit of convergence. Because we're taking the K through. Take the K through. So
Oh,
K through cancels the K power.
Right.
It just gives me a limit of 1/3.
yeah, so it's.
I probably wouldn't do the K through test here. Because this one doesn't have a K power.
Right.
Now I'll do it here. Cancel the K powers. And we get 2 squared root of K. It's the limit of 2 squared root of K. So that's a little smaller than 1. So it's convergent. This one I would just do a test for divergence. Right to the K, it's faster than K squared.
Right.
Test for divergence. Do you recognize number 7? If you wrote out the first few terms, do you see what's happening there? Write out the first few terms, starting with K is equal to 1. Write out K is 1, 2, 3, and see what kind of pattern you see here. So the subtraction is kind of a hint. Keep them separated instead of putting them together. Keep them separated. Sum, right up the terms, and you see, right up, so it's in there. Actually, K partial sum, S, sum, A. Figure that. That's what it is. Okay, we'll catch up with you then. So the first one, I see that K power on everything. So that's a great candidate for the K root test. It says take the limit as K goes to infinity of the Kth root of the AKs. So in this problem, the Kth root is just going to cancel that big old power out there. know that looks like a lot of steps. At least this way you show me that you know what the kth root test says. You can take the kth root of the general term. So here's the kth root of the general term. Knocks these guys out. I take the limit and I end up with 1/3. Just like with the ratio test, we compare the size of the limit to 1. If it's smaller than 1, it converges. If it's bigger than 1, it diverges. If it's equal to 1, you try something else. All right, so when I see subtraction, this is me. This is me. This is my nose. I'm smelling. Smells like it's telescoping. That's great art right there.
Should have been artist.
Should have been.
Are you teaching calculus?
Art sounds like work. Teaching calculus is easy. All right, so I'm going to write out the first few terms and prove to myself that it's telescoping. So when k is 1, I have 1/4 minus 1/8. Does k start at 1 on this one? Starts at 3. I think I saw anybody starting at 1, so let's start at 3. So this instead I have 1/12. 12 plus 4 is 16. Now k is 4. And I get 1/16 minus 1/20. Now k is 5. And I get 1/20 minus 1/24. So it is telescoping. All these guys will add each other out until I get to the nth term. And the nth term will look like 1/4n minus 1/4n plus 4. And the pattern will continue where all the inside terms will add out. So I get a closed form version of what the partial sums look like. If you can write your partial sums as a single formula, then if this sequence of partial sums has a limit, then the series converges to that same value. So I put these two together and look at the limit as n goes to infinity of my nth partial sum. And I get a finite limit. So my conclusion is the sequence of partial sums converge to 1/12. So the series converges to 1/12. Real hard to write the partial sums unless you've got something that telescopes. All right, you guys want a little break? We got time to take a little break if you want to go stretch your legs. Uh-oh. The wrong thing on the back of these. I made a blunder in copying them. Some of you got this mutated version of this. Sure enough. Backside doesn't look what it's supposed to look like. Sorry. You've got part of the series review and part of the series worksheet. So your back should look like this. Does anybody have that on the back of their sheet? You don't. It's just supposed to have problems on the back side.
I've got one.
You've got one? I've only got 3. That's that, yeah. You got the right one? The back side, yeah, you got that. Some of them I've copied. No, it should look like this, like this one. Anyone? You got back side, it just looks like problems? Some of you, the back side looks like that. Yeah, so you need one. Yeah. Sorry. got any more up here? I totally mucked that up, didn't I? Oh, here's some more, here's some more, here's some more. Well, that happened. Okay. These can go in the garbage again. It's bad. Quickly running out of semester. You realize that. In fact, you've got another test coming up. When?
27.
27. The period of no exams, that 1 week before finals, starts on the 28th. So we're not moving that test. It's staying on the 27th unless you want it earlier.
How much more stuff do we have to learn?
What we just did today was section 8.7. In section 8.8, we're going to do Taylor and McLaurin series. And then 4 sections of chapter 9, we look at vectors. Vectors in 2 dimensions, vectors in 3 dimensions, how to add, subtract, multiply vectors by a scalar, and the 2 similar operations to multiplication would be a vector dot product and a vector cross product. Does that sound like anything you've done before in your lives? Anybody do vectors in physics? So it's just kind of setting you up, because calculus 3 is multivariable calculus and vector calculus. So you begin calculus 3 doing the multivariable part, and then once you get into, I guess, chapter 9, you're going to start doing vector calculus, which means you're going to take a derivative. You're going to interpret what the derivative of a vector means. You're going to build things like tangent planes and normal vectors, and just do all kinds of calculus.
So we're gonna have 12 sections for next time.
You guys can come in to learn a lot of content. You want to just stop content at the end of chapter or whatever? What are we on, chapter 8?
Cut it off.
I can cut off. I can do you test on chapter 8. That's no problem.
Right.
8 sections of chapter 8 are on exam 3. And then we'll put the vector sections and the comprehensive stuff on the final.
Make your finals hard.
It's departmental, so Dr. Williams makes the final. Everybody takes the same final.
Dr. Williams makes it hard.
Yeah, we have
Just
some
answer my
final.
question there.
What do you mean?
I have a friend that's in calculus too, but it's like with a different professor.
And?
And her tests like are easier. But this is on.
Because you're honors. I get to ask you things a little bit more than I ask my non-honors people.
So hopefully the final.
Like on my regular Cal 1 test, I'd say, what's the derivative of x squared? And I would never insult my honor students with that. Because then my non-honor students say, oh, that's so hard. I didn't know this was going to be on the test. And honors like, come on, bring it on, baby. This is a question you're going to ask me. I'm going to ask my own questions. Ask that one out.
Right.
Studying for the last test with some of my friends who are in like non-honors section, I pulled out your review and they're like, you've never done anything like this. It lasts a lot.
So is the final going to be easier because it's made by somebody else? Like, if you make the final review.
I'm taking a beating here. You see one calculus test, you see one. Except for you guys are disagreeing with that. I'll show you some, I'll post some on Blackboard of previous semesters. Dr. Williams has written the calculus final for so many semesters in a row, and you'll see that they're not any harder or easier than what you've been doing.
Got one last semester. Our final was like 10 times easier than you are. Right.
Multiple choice.
We got to the final in multiple choice, and I did it in like 5 minutes. I was like, all right.
I didn't give that Calvin final.
Oh,
I live in Tulsa, they're intelligent.
You gotta punish them. That's why.
I did not give you that. I didn't. I hate multiple choice tests. I hate them with a passion because students will get the right answer by doing the wrong work.
Right.
What is f prime of 1? It's 0. They got 0 because they screwed up the derivative, but in fact, that was the right answer. So I hate giving giving points for the wrong work. So anytime I get multiple choice tests, as the departmental test, I just get on my computer and I complete all the choices. Show me your work.
Well, at least I got a partial credit.
That's right. You got the wrong page. Okay, so there's the next 3 problems. If you don't have those 3 problems, I copied your problem pages wrong. I got a few more that are done properly. Yeah, no. Turn that over. Yeah, we're gonna see it. Oh, that's what it's supposed to look like. Okay, so starting on number 8, it's kind of a clue when you see multiplication in k powers. There's your clue. Number 9, slipping that plus sign in there means don't do number 9 the way you did number 8. Right? 8 powers, multiplication, factorial, they're all pointing toward one test.
Right.
Their size is the 1.
Oh,
Bigger
yes.
than 1 is.
The limit, because that's where it's pretty constant.
That's right, yeah, keep them straight. No comparison to any limit is good. In the ratio test, you need your limit to be smaller than 1. It's hard to remember all those conclusions. That's why the more you write your conclusion as a sentence, the easier it is to remember. In the ratio test, the limit bigger than 1 means divergent. In the ratio test, the number 8. Bigger than 1 is divergent. Smaller than 1 is convergent. Equals 1 is do something else. You can't take those 2 pluses. That's the limit. That's the expression that is 2 pluses. That's for this. Okay. You want movement, that's 165. You can't do this thing. right, so here's what the ratio test looks like. So my k plus first term divided by my kth term. Cancel 3 to the k, that one. 2 to the k, that one. And I have left 3 to the 1 times k on top. 2 times k plus 1 on the bottom. So my limit is 3/2. In the ratio and the root test, we compare things to 1. That's bigger than 1. Bigger than 1 is divergent. Okay. Run the test. State your conclusion. Has anybody tried number 9 yet? Anything, the plus sign here keeps us from doing a ratio or a root test. So if you're going to do something, don't do ratio or root. If you're going to do something, which of course you're going to do something. So back to the little nose picture, can you kind of start smelling things that are going to diverge? Does that one have that smell to it? Why? Why do you think number 9 is going to diverge, other than my hint? It's top heavy. 3 to the k grows faster than both 2 to the k and k squared. So it's top heavy. That means its limit's not from 0. So in our test for divergence here, we can show that the limit is not 0. So when we look at the 2 terms on the bottom, this one grows the fastest. There's only 1 term on top. So when I look at the ratio there and taking the limit, 3 to the k grows faster than 2 to the k. So the limit is infinite. If the limit is not 0, the series diverges. Okay, so again, here we've got plus and minus signs, so I'm going to stay away from ratios and root tests. And it's not top heavy, so the test for divergence doesn't help me here. So that leaves just a handful of tests left. Things that are added together, I try to compare it to something. Whether you do a direct or limit comparison test, knock off the constants, see what's left, that's your comparison series. Does your comparison series converge or diverge? And how does it behave with either a direct comparison or a limit comparison? Try something else. So that's what you try. Okay, so if you're stating here that this is a convergent p-series, don't assume that the reader knows that. Tell me.
I did say it, but I guess not.
I don't think UK does as well. Simplify it. That's k to the 1/2 over k squared. Write it as 1 over k to a power. And now that's a known series, right? And you have gone the wrong way with the direct comparison test, right? Bigger than convergent is not convergent. So you're forced to do the limit comparison test. Any positive finite limit means both series do the same.
Zero.
See divergence?
Right. Bigger than one.
This is the, any positive finite limit means both series do the same.
Well, like, I don't have to do the series of these.
What kind of series is this? With p bigger than 1, so does a p series converge if p is bigger than 1? Converges. Converges. P is bigger than 1, it converges. Think of the integral test.
That's like one or less.
1 or less diverges for a p series. We're going to try compare. I just threw away the numbers. I threw away the 4, I threw away the 2, and I can simplify that as 1 over k to a power. I got a k to the 1/2 and a k squared. So 4 halves minus 1/2, this is 1 over k to the 3 halves. So that is a convergent p series because my p is bigger than 1. P smaller or equal to 1 diverges, p is bigger than 1 converges. Now when I constructed this, I made my numerator smaller and my denominator bigger. So I made my BK smaller than the AK. So it's going the wrong way for the direct comparison test. So you're forced to use a limit comparison test here. Take the limit of your AKs over your BKs. And if you get a positive finite limit, they'll both do the same thing. If I look at this product here, then that product is like a k squared, and that's a k squared. The other terms are lower in degree, so the limit is just going to be the ratio of the coefficients. So in the limit comparison test, any positive finite limit means both do the same. So the series converges. Positive finite limit means they follow each other. They either follow each other in a divergent way or in a convergent way. And this one, they both converged. Oh, I wrote that too far over there. Nobody's watching anyway. You have to go back to this video, pick up what you missed. You got to do a lot of speeding ahead. I'm going to post the written solutions online as well. So if you're missing out on any details, I'm going to post all of the solutions. So the next three. Let's see, we went through number 10. Do we have time to finish them? Yeah, let's hustle. Next three. So in number 11, you're tempted to use the kth root test, but the limit's going to be 1, and that's the case where the kth root test is inconclusive. So try something else. A couple of ways you can do number 12. Number 13 is a quickie. Number 11 can be quick. Number 13 is quick. Number 12 can be done several ways. It's going to work, so try it. We're taking a look at the general term, doing the test for divergence. That's better. Better.
The only way.
I want you to do it.
Because they tried for like the root test.
The root test gives you one. I think the ratio test is going to give you one. So do the test for divergence. Do the test for divergence. Show me that the limit of that thing is not going to be 0. You're doing the test for divergence here. Can you show me that the limit of your kth term is e to the 7th? Can you show me? Can you show me the in-between steps? But if it's a known limit, I'm fine. But if you guess wrong, then you guess wrong. I'm glad that you recognize the limit is e to the 7th. Okay, I'll take that. I'll take that. But if I say show me, if I put that in the sequence form and say show me, I want to see the steps. Right? You know, because one day you're going to be a mom and a dad, and your kid's going to be at college, and they're going to say, can you help me take the limit of this? You can't just say, oh, it's e to the 7th. No, you want to bond with your child. No, you put your arm around and you say, here, watch this.
Tell them to go to the calculator.
They're going to come to you because your mom's going to say, Dad's an engineer. He knows how to do calculus. I'm an art major. Here, let me draw somebody smelling a series. We have the neighbor's kids coming to our house. My mom said you could do to me. There's some muffins. Oh, okay, I do it for food.
My parents stopped being able to help me with math at algebra too.
We'll see, but you're not going to get there. What Dad didn't even graduate from high school. He couldn't help me with my high school homework. He said things like, what are you going to school for? I'm join the army. Almost did. I was so scared of guns. I'm so cool on getting dirty. Everybody dies for oil. And dying for oil for all of our lives. Right, it's getting tiny. Almost there. What's left? Let me see what's left. Yeah. No idea. It's nothing wrong with it. 3 or 1. It's a hard one to do the ratio test on, so for this one, let's do the K fruit test. Does anybody have any suggestions for number 12? Anybody trying anything on 12? Comparison test will work, right? Because our logarithm's at the bottom of the old food chain there when we talk about tower power. What's right above a logarithm? Square root of k. You can always compare a logarithm to the square root of k, and you can do some sort of comparison test. When I see a logarithm and a 1 over k, I always think an integral test too. Either one of those will work pretty well here, using the fact that the log of k is smaller than the square root of k. So you can build your bk series by making your denominator bigger. So while you're doing that, I'm going to go through all the steps again to show that the kth term here goes to e to the 7th. One to infinity is an indeterminate form. It's not 1, it's indeterminate. So that's where we set it equal to L and then take the log of both sides. Put a logarithm right here and here. And pull my k down here. Now it has the form of infinity times 0. So in the next step, this goes underneath as a 1 over k. Now it looks like 0 over 0, so I whip out the old L'Hopital's rule. L'Hopital's rule, I take the derivative of the top and divide it by the derivative of the bottom. The logarithm of u is 1 over u. And I go inside and take the derivative of that. That's the derivative of the top. Here's the derivative of the bottom. So the negative 7 over k squared cancels with the negative 1 over k squared and leaves me a positive 7. And that's on top of that 1 plus 7 over k. That's the only term that has a k. When k goes to infinity, it goes to 0. And that tells me that the natural log of my limit is 7, so L is e to the 7th. The limit is not equal to 0, so series diverges. Be sure to state your conclusion about the series. A lot of steps, but they're good to know. It's also good to recognize that this e to the 7th. Good. Well, we saw the Q log there. It itself is not a Q log, but you're going to compare it to a Q log. Because the plus 1 makes it not a Q log.
Okay.
But it looks like a Q log, so do one of your comparison tests with a Q log. Yeah. This is how it diverged.
Cool.
Yeah, it's going to converge.
We can, 11K cube, I make it small.
Yeah, let's look. We're going to compare that to, let me pick my BK. 3 over k square root of k cubed. So now I made that bigger, which means my BKs are smaller than my AKs. So AK is bigger than my BKs. Right? You just row. This is divergent T series. If you do 0,
That's what's kind of, I was kind of doing that.
you're doing the limit comparison test.
I was, but then, I changed the
Direct comparison test.
Correct.
But you made this is smaller than that, smaller than divergent is no divergent. Bigger than divergent.
Oh, right, yeah.
Okay? So I don't even think, I don't know that that's going to work either, because the 0 case has to be compared to the convergent.
Yeah.
So maybe a comparison test doesn't work. Let me look. Let me look if I can do a comparison test on 12. Integral test works easy. This is a convergent series. If you integrate it as a u/du integral. But if I try to compare it, I'm going to say, here's what I found. Gosh. Does she not do that every class? That is smaller than this, right? And so flip it over and stick a 3 on top. But this is a p-series. Let's see, that's k to the first, k to the 3/2.
She gets ln k squared.
It should be a square?
Yeah.
Oh, okay, and that changes my power, but it's still gonna be a convergent p-series. Because that gives me now a this is a convergent p-series. And bigger than convergent doesn't tell me anything. So a direct comparison test doesn't work. A limit comparison test is going to be infinite. I tried the limit comparison test by taking my limit of my AKs over BKs. I'm going to have an infinite limit because the k grows faster than the log of k. I don't know, let me do the L'Hopital's rule. Maybe they grow at about the same speed, let's see. It's got infinity over infinity, I'll do L'Hopital's rule. Times 1 over k puts me a k up here. Nope, that's going to be infinity. So the limit comparison test doesn't work either. In the infinite case in the limit comparison test, you need this guy to be divergent. So I take it back. Comparison tests don't work here. You got to do you an integral test. But it's easy to integrate 3 over x, natural log of x squared. Take u to be the natural log of x. du is 1 over x, so you're integrating u to the minus 2 du. Show me that that integral converges, and that'll be enough to say that the series converges. So you're integrating u to the negative 2, and you get minus u to the minus 1. I don't know what it went from 1 to infinity, 2 to infinity. Let's go from 2 to infinity. So we get, when that's infinite, I get 0. So I get that my integral converges, so the series converges. Did you have something better to compare it to? Is anybody able to run a successful comparison test to show it converged? So I'm going with integral test. Number 13, did you show that converged with the k through test? You take the limit of the kth root of that, which gets rid of all of the k's. All of the k's that are powers. Then what's left has a k in the denominator, so the limit is 0. Any limit smaller than 1 means it converges. That leaves us 3 more. And 5 only minutes more. So let's see if we can pick our way through these. Number 14 almost looks like a Q log, so compare it to a Q log. Throw that one away and compare it to a Q log series. But decide what Q log series does. All right, so number 14. Compare it, do some sort of comparison test. But tell me what this Q log series does. The next one, K powers and factorials. So 15 should be a ratio test. Number 16 was the first one that we encountered that had negative terms. So let me change the instructions on 16. I want to know, is it absolutely convergent, conditionally convergent, or divergent? And just for the sake of time, show me that it's not absolutely convergent, but it is conditionally convergent. If anybody's gotten any progress, I'll be glad to look at your stuff and see if you did it when you need to. So include an absolute value, 1 over 2 square root of k, because we compare it to, which is the p series. Compare it to, right. So we're going to do a comparison test with p series without the negative term. And that comparison test should show that it's divergent in absolute value. We'll do the alternating series test to show that it converges with the alternating. Is convergent, that is convergent by the integral test. Just try integrating 3 over x, dash log of x squared to be d substitution. Interval of convergence, series convergence. Smaller than 1, so we got it. Bigger than that, we got it. Perfect. You love diverge when p is smaller than 1. You did. Okay, that's what I thought. That's what you benefit having messy handwriting. Yeah. We're going to swap your homework with me and put that on that table. Good. All right. How do we get a high number? Thank you. And if this page has helped you in any way and you want to go back and reopen some web works and try some of the ones, Let me know, I'll be glad to open them again. These are Q logs, that's divergent. Bigger than divergent is divergent. Good. Rather than 0, the ratio is good. Why isn't it absolutely convergent? It's kind of, you're going to compare it to a divergent Q series, maybe with a comparison test. But this one isn't an alternating Q series to compare with. The alternating series test should be when it goes to 0, the non-alternating part, and then it's decreasing. This is an absolute value if you're doing a ratio test. Which means that's one and it's not conclusive. No. It's not conclusive. Not convergent, not divergent, not conclusive. I don't know.
I thought there was only to do that.
Even if you can't do the ratio test on the non-positive term test. So you do the comparative absolute value to 1 over 2 squared of k. So an absolute value, you do the absolute convergence test. The absolute value because minus 1 over k compared to 1 over 2 squared of k. So for the sake of time, let me do the 16. 16, I would want you to check this. So first you check for absolute convergence using just the absolute value of the series. So if I take the absolute value of the series, I just lose the negative part. And so I'm going to do a limit comparison test with the series 1 over 2 square root of k, because that is a divergent p series. And in my limit comparison test, I take the limit of my given series with my comparison series. I get a limit of 1, so they both do the same. So it's not absolutely convergent. It's not absolutely convergent. The next thing I do is the alternating series test. I show that the limit of the kth term goes to 0. And I show that it's decreasing. K plus first term makes this denominator bigger. So the overall fraction is smaller. So as I go to the next term, the AK plus 1 is smaller than the AK. So it is decreasing. So that makes it conditionally convergent. Okay? All right, ratio test will show that this one's convergent. And when you do a comparison, either comparison to this divergent Q-log series, you can show that that one diverges. So again, I'll put the write-ups to these on Blackboard if you need to get all the details in. If you have any other questions, just let me know. Otherwise, have a great weekend.
You too.
And I've got some homework up here if anybody wants their homework back. Derek, Lucas is only here every other day. Lucas like every other day. I can never give his homework back. Braden, did Braden leave me yet?
I'm right here.
There you are.